Welcome back to Roid Rage. This is episode 28, and today we're digging into the part of the simulation we all pretend to know, the CAD modeling. We're here with Holly.
Hello.
Holly is one of our design engineers, and with my other special guest, Robin.
Oh, I'm special now?
I had to give you some credit. We have kicked Chap off the show. Chap is actually in Montana right now in a hole in the ground.
I mean, who cares?
Yeah, that's true. Who cares? All right, moving on.
It's planet Earth.
Holly.
Like, I'm not about planet Earth.
Yeah,
Let's go.
fair enough. Fair enough. Holly, you want to give us a little bit of background on yourself?
Sure. Yeah, I've been at AstroForge now for about 5 months. Before that, I did my undergraduate work in aerospace engineering at Cal Poly Pomona, and then my PhD defense. I went through that whole process, which was a fun process. I have Virginia Tech, looking mostly with in-space assembly work, looking at the structural analysis behind that and figuring out how we build things in space, and some fun interactions between when a structure breaks down and investigating how we can put it all back together. And now I'm here working on doing all our structural modeling to make sure we actually survive the operations we want to do.
So let's jump into that. When it comes to structural modeling, I guess give us the whole point. Like, why do we even bother? Why don't we just build the spacecraft like Kelly Johnson did in the 60s?
Stop trying to cut corners, man.
Yeah, you could build a spacecraft that survives pretty easily, but you're over-engineering it because you could make a very dense, very heavy box, throw it into space with a 90% success rate, and you're pretty sure it will survive. But A, we don't have that mass allowable. B, we want to make sure that it actually behaves like we want it to behave. And so going through the structural analysis, we get one shot at this. We're sending a spacecraft up. If we were doing this for a car, we could test drive 1,000,001 cars on the street, see what works, see what doesn't. We don't get that option with a spacecraft. We get one shot to launch it, and we can't launch a bunch of practice spacecraft. So we do that simulation-wise and do that digitally to make sure we can survive all of the cases we're going to go through.
But we don't just get one shot to launch it. We still test it. We still do vibration testing.
Absolutely.
So why not
And TVAC
just
testing.
I'm trying to see how we can remove structure engineers.
Oh,
why
trying
not?
to see how to fire me, I see.
Yeah. Why not just build it and then go into structure testing? Why not just go vibe it?
Because you're going to break it immediately. Structures testing is a very expensive process. You have to rent out a space a lot of times. You have to go through that process. You have to set up so many tests, and you want something to compare it to because you're never going to test every single scenario that you are launching the spacecraft through. You're going to be testing quite a few of those scenarios across a wide different variety of vibrations tests, but you still want to be able to have all the in-between cases survive as well. And I'm going through 1,000,001 different models trying to see what we're going to do. We're going to be, hopefully, vibing one of them, two of them. We're not going to be vibing 1,000 models that I'm running. So we want confidence walking into the structures vibe and the fully integrated
Robin, why do we
vibe.
have 1,000 models?
I'm just letting her.
You're just letting her go?
Yeah, I'm
Yeah.
just letting her go because I'm like, oh, this.
Taking notes like
Mhm.
1,000
Yeah.
models. What's going on?
That's a hyperbole, but I'm running a lot more models every single day than we would realistically walk into a vibe with. And I want to make sure that it survives going into vibe. I don't want to walk into vibe, shake the spacecraft, and it breaks at the first moment.
Yeah. Well, I'll tell you one reason we don't have well, it's probably not 1,000, but one reason we don't have just one model, because the level of fidelity that would be required on that one model, you wouldn't want to pay for the compute on.
Yeah,
Like,
absolutely.
so there's different models because there's different things that Holly's looking for, and there's more. You don't necessarily need that full fidelity for everything, and the way that you model it ends up being a little more efficient in one way versus another. So I'm very sensitive to cost of compute these days.
So let's, so we, help me understand, first off, why do we do the modeling? So I understand the modeling results to launch loads. What are you getting out of this model? Other than cool pictures we can send out and, really cool 3D drawings of the spacecraft, like what are you checking for?
Did you
What are
just say
running
3D
against?
drawings?
3D drawings. 3D like images, right?
Oh, man.
Yeah, there's a lot of things you look at in modeling. To break down what the modeling is we're basically taking the spacecraft and discretizing it down to a bunch of pieces. So you look at the model at like An atomic level, there's 1,001 atoms in it, all behaving a certain way. I'm not going to sit here and model every atom, though. So I basically kind of break the spacecraft down into pieces and say, okay, these 1,000 elements, these 1,000 dots and node connections represent this element. And so now I'm only looking at 1,000 instead of a billion trillion atoms. And so I get calculations at each one of those interaction nodes. The main things I'm looking for, first and foremost, stress. I want to make sure that when
I think Matt provides all the stress that you need.
Hopefully,
fair,
that's my job.
Fair.
Yeah.
Yeah, there's model stress and then there's Holly level stress. That's
Both are Maximus.
They're actually, yeah, I was
Both are
going to say
maximum.
they're actually
They're
kind of correlated.
actually.
Yeah.
Absolutely.
Oh.
And so I'm looking for stress in the model. I'm looking that when we deploy this wing that's going, this solar array wing that's going to create a stress at that joint and going to create a shock there, I don't want the wing to snap off when we deploy it. And so I want to make sure that all of the connections there can survive that shock.
That's not really going to happen, right?
No, it's
okay,
not.
I'm just checking.
It won't, I promise.
At least not in the model.
Theory. At least not in the model, which we'll get into.
Great. One more thing for me to
So
go
I'm
look
looking
into.
at stress in the joints because every single material has a set amount of stress you can put in it before it either, deforms past the point of being able to survive that or breaks entirely. And I don't want it to get close to either one of those locations. Additionally, things I'm looking at are vibrations. This model is going to be shaking at certain frequencies on its both natural frequency and how it vibrates just at its base self, and then excitation frequency. The spacecraft is going to go through a launch window where it gets a lot of vibration put through it, and I want to make sure that it's not shaking itself apart. So I'm looking at how it behaves under vibrational loadings.
So I know the structures team cares a lot about all these tertiary things.
Mhm.
I just care about if SpaceX allows us to launch it.
Yeah, that's
What
big
is the
thing.
minimum we need to build for SpaceX?
Yeah. So we can't break. We have to provide.
Wow, that seems like a really, really low bar
That's
for
a-
I could
everything
do
else.
that
you-
without CAD simulation. I'm pretty
yeah,
sure.
yeah. Just don't break.
Okay.
Yeah,
Yeah.
so we can't break. And so we have to have a base number that has a factor of safety to it. So say, we are aiming for this number to not break
What is our number?
for
What's
the
our factor of safety?
safety?
Yeah.
Factor of safety for SpaceX RPUG, I believe, is 1.1 to yield and 1.25 to ultimate. NASA standards is 1.2, I believe 1.25 to yield and 1.4 to ultimate.
What do we do?
I'm holding those as best as possible on all the areas.
You're holding NASA standards as best as possible.
Mhm.
Sounds like we got some mass we could take out, Robin.
But I already told them I was going over there with a drill if they didn't get the mask done.
Okay.
absolutely. Absolutely.
Wait, but okay, Matt, you just asked about SpaceX like they're the only game in town, right? I mean,
Has anybody else given us an RPUG to go launch to?
okay, next topic.
Yeah, so every RPUG has set standards that you
Wait.
go to.
What was the RPUG again? I don't think we actually defined that acronym. I know how much you love acronyms, Matt.
That is right. That's my bad. The Rocket Payload User's Guide. I think it's downloadable and public to everybody.
It
if
is
it's
public
not,
information.
is.
okay, good.
Yeah,
I mean, not like
otherwise
don't
we would
talk
have had to
about shit
chirp
we're
it
not
out or
supposed to anyways,
something. Yeah.
Yeah, so it is public information. And so that's some set standards for like static loading conditions.
What about frequency?
For frequency, we have to be above 40 hertz. So everything kind of vibrates at natural frequencies. This is a modal response we're looking at. We have to make sure we're not in the range that the spacecraft could vibrate and break things with, because then you get some resonant frequencies and it goes bad.
We can hear 40 hertz, can't we? I mean, it's pretty low, but
I believe so.
I do not think you can hear 40 hertz.
don't
really?
know.
Rachel,
Can
do you
hear-
know? Can we hear 40 hertz?
Rachel, can you
I don't
ChatGPT that?
actually know.
If we can hear 40 hertz, I want to insert a 40 hertz tone right.
Let's just put
Here.
one of the. We should get. Okay. That's,
Why are you talking? I wanted it right here.
Yes, humans can hear 40 hertz because the normal human hearing range is from 20 to 20,000.
Yeah, 20,
20 to
20,000.
20,000.
All right, let's
So-
put in a 40 hertz tone,
We
right?
could also just get a metronome in the
Here.
structures area that just clicks at 40 hertz. I'll
that
order that.
sounds like torture.
Okay.
You know,
Um,
I actually bought a ultrasonic cleaner, and when I was at SpaceX, it was all like one building, one office, or all that kind of stuff.
Mhm.
And the ultrasonic cleaner, it came in to clean the parts, and all the engineers were super happy that the parts are getting cleaned. And it was like awesome, except that there was this background din noise that like irritated everybody in the building. And like we actually had to get another building.
Oh, God.
Like
That was the solution. Buy another building.
well, we were
What a
expanding
wild
anyway,
solution.
but yeah, no, seriously, like that level of irritation just drove everybody nuts. So
Mhm.
you know,
It's a good- it's a
I don't
good
really know
note.
how that
Fair.
relates, but you know,
If they're not working hard enough, we can just get ultrasonic cleaners. What I'm hearing.
well, really, I'm trying to prevent you from putting a metronome next to the stress people because they're pretty stressed out right now. Because
Yeah.
Why are you stressed
that was
out right
last
now, Holly?
episode. Yeah, what are you stressed out about, Holly? What are you
Yeah, I
worried?
think the main things is making sure our spacecraft survives. A, big stress.
Right, so don't break. Okay,
Um,
yeah.
B, I want to keep making a model that is more and more representative of the spacecraft because usually you start at a very
So let's talk
simplified
about that.
model.
How do you start? So yeah, we're talking about this. Obviously, the spacecraft starts off as a box.
Mhm.
That's what it looks like.
Yep.
Walk me through how you've progressed it from a box with 6 sides to what is now our spacecraft. What is that? You mentioned thousands of models. Like, how are you thinking about it when you design to make sure we hit 40 hertz? We have
Or
a
greater.
1.4 factor of safety, right?
Yep.
We're not going to
Or
break
greater.
off. Even, right? You violate the requirement if you go greater too.
You do.
How do you think about that? How have you structured this out?
Yeah, so when you break it down, Vestri is just a box with some wings on it. And you can start it from a box pretty simply, just throw it together. A cube is, you can represent a cube with 8 nodes. You're never going to do that though. When you actually break it down, I started out with kind of the model I inherited was a set full finite element model where all the components are defined in the same file. And so what I decided
Is
to
that
do,
good or bad?
it's neither good or bad, but it is
Sounds bad.
it
Sounds
is
bad. It sounds like it's neither
challenging.
good or bad, but it sucks, and here's why.
It's
Yeah,
a, it's a fine model for that stage of it. It's hard to iterate past that because let's say something changed in the component. I just want to swap out that one component. I want to swap out that battery for a better battery. I want to swap out that piece for something greater. I can't. And so the first thing I did when I came in here was I made a reconfigurable model.
That is the most engineer thing I've ever heard, because this is what engineers do all the time when you bring in new engineers.
They
They come
redo.
in and they redo whatever the other engineer did.
Yeah.
That's fair.
It's pretty standard.
It's pretty standard because you don't really know. There is a style to doing the engineering, whether it's an FEA or
Mhm.
other kind of like. I mean, you clearly have opened up spreadsheets from other engineers, Matt, and been like, "What were
Trying
you
to read
thinking?"
someone else's code.
Yeah, it's really hard. But anyway, yeah, no, that's a total engineer thing. Always. Well, the first thing I have to do is redo everything. Oh,
Yep.
thanks.
Who gave you the model,
Yeah.
Holly? I remember
Eric,
this is Eric.
Eric originally gave me the model.
Oh, that thing was messed up.
Oh, that yeah.
Did
It
we?
was fine.
Did we do the? Oh, it was fine. Yeah. No, did we do the performance improvement plan yet on air
For Eric or Holly?
or Ashton?
Ashton should have been on top of it actually as we talk about this. Yeah, you're right.
Yeah,
So,
totally.
yeah.
We talked about that a lot last episode.
Let's add this to his one from last episode.
Right. Okay.
Yeah, so when I started with the model, the first thing I started with was the base
Wow.
plate.
Look at that. She just moved on. That's
I
awesome.
did,
Yeah, that's
yeah.
great. Just
I
segue.
mean, feel free to interrupt at any
Non-
point if you want to do my performance
don't-
review, but I'm just going to breeze right past that and not give you the
Non sequitur.
opportunity to give me one. And so, starting with the base plate, all
What
the
it's
forces
like to work in
in
a
the
startup.
spacecraft go through the base plate. And so it's our biggest load path. And so that was where I really wanted to focus at first. We had a version of the base plate. We were looking at machining
It was too heavy.
It was too heavy. It was honestly a kind of rough form factor for a lot of reasons. And so what I did for
What
the very,
base plate did you get? Did you get a square one?
I
Or
got the square one.
Oh, you got the fucking square one. Oh, Jesus.
I chopped those corners off. Yeah. And essentially I was given the base plate. And so I wasn't even looking at the box in the beginning. What I was doing was a concentrated mass model.
Concentrated mass model. Say more.
Because essentially everything on the spacecraft is a mass. You know, this mass is
Sounds like
sitting on this
physics.
area. It's all physics when it boils down to it. And so
Wait. I know where this is going. Ready?
Mhm.
It's a mass and we accelerate it.
Boom. Yep. And essentially I wasn't at the point where I needed to get a base plate out quickly, but I didn't have time to build up the entire spacecraft at that point. And so what's the easiest, most simple representation I can get of a base plate version? So we get some base numbers. So instead of putting a battery sitting on the base plate in that location, I'm going to create the concentrated mass of the battery. So take the 3 kilograms that the battery is, put it right on those attachment points in the base plate where it will sit and bolt in, put that mass there, and do that for every single component on there, accelerate the whole thing, and get its response. So instead of seeing, so that won't tell you what's happening on the battery side. So you don't know if the battery is safe or not, but you know what it's kind of doing to the base plate. So that was the first version I built up, was a concentrated mass version of all the masses sitting on the base plate, go through its quasi-static loading, see what it does.
Can't you just ask ChatGPT to do that?
In theory, for
Right.
simplified models, you could kind of get some base numbers, but this is such a complex
You know how many
problem with
companies have fucking
thousands of
sold me
nodes,
like,
thousands,
oh,
hundreds, millions
we can
of
take your CAD
nodes.
model and ChatGPT.
I wouldn't trust it either, because the thing
It
about
doesn't
it,
work, first off, but
Yeah.
yes.
Let me tell you, I don't trust human engineers right now.
fair enough. Well, the thing about it is there's so many choices in an FEA model where the common saying is garbage in, garbage out. If you make something incorrectly modeled, it doesn't matter whether it shows you its success or not. If you did not model it correctly, you cannot be confident in what it's giving you. And so that's on the human error side. There's no telling how well ChatGPT could really define all those things.
Yeah,
Let
was,
me,
And-
I was
let me
kind of
ask you
being
this.
funny,
So cool.
actually.
We're building up base plates, you add on walls, you do all this shit. We can all agree that we live in a simulation.
Okay.
What is different and what do you plan on between the simulation and actual manufacturing or building the base plate? Like the base plate we got, obviously it looks the same shape and direction. What is different from what you put through the simulation? How do you account for it?
Yeah. So when I first went through it, I am modeling the base plate with all those concentrated masses. I make it a more detailed version. Eventually, I have time to build up all of the components that sit on it. I get better interaction and I get a more quote unquote finalized model. And now I start working with Eric because he's making changes to the base plate and I'm simulating them. So he is going through, puts together a base plate. I run it through simulation. I see high stresses in one area. He changes the base plate so we alleviate some of those high stress. And we're constantly doing this back and forth dance to make a better version of the spacecraft. But when you actually go to manufacturing these things, me and Eric are negotiating through, I need 0.5 millimeter more there. I need a little bit more there to beef up that area to get you a little bit stiffer. But those tolerances are really hard to hit when actually machining something. And so when the first base plate that we were looking to fly came off the CNC machine, we had to send it out to get independently inspected for the carbonics ring holes because those carbonics bolts have to be within such a tight tolerance that we got that externally inspected. But internally,
What was the tolerance?
the flatness tolerance call out was a number that I
Half a
don't know.
thou?
Yeah,
Half a
that sounds
thou?
about right. 0.5 thou. And we don't have that on the rest of the base plate, so we don't really know. And so I sat down with a pair of calipers one day and measured multiple points on the ribs to make sure along this rib, this is what the thickness is. Because if we're targeting this rib's going to be 4 or 5 millimeters thick, is it actually 4 millimeters thick or is it 3.89? And what does that do to the model? And so then I can go back into the model, change those thicknesses and make a representative version of the bit we actually made.
So
and
let me
see how
ask you
that
this: like,
changes.
we're not going to be. I mean, there's always going to be a unit of resolution here. We're not going to be down across the base plate. How accurate are we compared to what you've simulated?
That's really hard to know in simulation alone, and that's why we're going to be going into vibe testing because you can correlate some of those
So how do you account for it
responses.
in either the way you do the design, the results you get, or in the model? How are you accounting for that, the discrepancies between the simulation and what you produced?
Some of it is included in the factor of safety. A lot of it is investigating your connections because the two things that are pretty much always going to be the biggest factors in whether a model is successful or not is, are your boundary conditions and connections correct? And is your material modeled correctly? Those are the two biggest things. And so you have
Can I add whether or
Yeah,
not you had
go
the
for
right
it.
load cases to test as
Okay,
well?
I was factoring that into boundary conditions.
right.
But yeah, loading, because the thing is,
Holly, what the fuck is a boundary condition?
so a boundary condition is basically how you're
Matt,
fixed.
Matt doesn't know anything about boundaries.
Yeah.
So a boundary condition is basically how you're relating that piece to another piece or to the real world. And so you look at even this chair. This chair is on the ground. If everything goes according to physics, it's not going to pass through the ground. There's a surface to surface connection there that allows the chair to not go through the ground. And so it's modeling those things. It is looking at the fact that I have a bolt in a hole. How do I model that bolt? Because you want it to be representative of the fact that that bolt is made of a material, and that material is not infinitely stiff, and it has to respond with the material properties of that bolt. What faces is it actually connected to? What things is it grabbing and connecting? Is it a threaded connection? Is it a bolt with a nut? Are you able to have slop in that joint because maybe that fixture isn't completely rigid and there's some tolerancing there that allows for some, slop in the system? That's a boundary condition. Things like hinges being able to open. It's fixed in multiple degrees of freedom, but it still allows you to open on that one specific degree of freedom. What's fixed, what's pinned, what's on a roller.
Man, what did they do? What did they do in the 60s when you couldn't have
Yeah,
all
You had to
these?
hand calc this all. There was also, pretty advanced, punch card computing systems that you could go through as well.
Yeah, but let's be honest here for a second. Let's go back to the V2 rocket. Like
Mhm.
there was no computers. I don't even know if there was punch cards back in the 30s,
You
right?
seriously don't know?
You had human computers.
You did have human computers, sure, but they're not doing any kind of finite element analysis on any kind of. I mean, those payloads were bombs, so probably not great. But when we
Get 'em.
sent up
Get 'em,
Sputnik
Ollie.
or when we sent up Explorer 1, like there was no finite element analysis at that time. And sure, you could do some rough hand calcs. How did they design these? How did they think differently about the?
You can still do these at pretty high level hand calc solutions because everything you're doing in a finite element model is all the same base equations. So I'm calculating all of the same base equations I would do in hand calcs at every single node. Your model gets coarser then. So instead of representing it with thousands and millions of nodes, maybe you're now representing it with 100 nodes and you have to calculate all those hundreds of nodes out. Maybe you do that by hand. Maybe you have a punch card system for going through that. So it's still all the same base equations. Physics is still the same. It's just the fidelity and resolution you get out of your model.
Wow. I just heard we're always going to need faster computers.
Fair.
Yeah. So what like still, I'm not really getting a great answer here in my opinion. It's like,
Okay.
why the fuck do I use a computer? What advantage am I getting from having higher fidelity models than from doing it with hand calcs?
Yeah. So when you look at it, so let's say you're looking at a model that's represented with 16 points versus 4 points. You have 4 degrees, 4 times better resolution in this model with the 16 points versus the 4 points.
That's how math works. That's good. I know that formula.
And let's say you have a stress concentration on 1 point only. When you have 4 points, it's going to take the surrounding nodes and kind of sum them up, and you're not going to get that fine detail resolution. It's like looking at an image. What's the resolution of an image? Maybe you're looking at a face in low resolution. You're not actually going to be able to tell what is the shape of the nose. What do their eyes look like? You might get some colors, you might get some base features, but you're not going to see the fine detail resolution because the image is too mucky because you don't have enough data points. And so by having a higher fidelity version of the model, you actually see what's happening at a finer resolution. And with that, you can identify there's a stress concentration there that would maybe get eaten up by the fact that it's being kind of averaged to the elements around it with a more coarse mesh.
Cool. So I know where my stress is with more.
I think she's saying
detail.
you can make it lighter.
Is that what we get out of this? Is like at the end of the day, we can just make a lighter spacecraft. Like we can always, I guess, overbuild it if we wanted to get rid of that stress. Is that a fair assessment?
Yeah, and maybe you have a specific point where you will fail because you have a high peak stress concentration there, and because your model was too coarse, you're not going to see that you fail there because you've kind of summed it into the surrounding elements, and you'll never know it's there.
So
if you don't
greater
go fine
confidence,
enough.
lower safety factor.
Exactly.
I mean,
Very
so back in the day, is it built heavy ass spacecraft?
That's also true too. Yeah, a lot of
That-
times you over-engineer
Actually,
it.
that is
That
true.
is actually what
Yeah,
happened.
I mean,
No.
Sputnik was a ball with 4 antennas, right? So it
Mhm.
was pretty easy to. That was just one element, right?
I think their radio worked better than. Oh no, let's not go
Wow,
there.
that was cold. That was fucked up, Robin.
Yeah.
But it, to be fair, it did.
Yeah.
But yeah.
Okay.
Oh, go ahead.
Why else do we use this? So cool. We can get better resolution. We can make it a little bit lighter.
Well, you like the pretty pictures, Matt. Let's face it.
I mean, but that's not part. That's not part of Hawley's fake simulation. I don't like those ones. We do the rendering, and those look fucking cool. But those always take hours for some reason.
Yeah, models can take a significant amount of time, especially when I'm looking at the full spacecraft. There's ways around it to make it run faster.
His
But-
problem would be solved with a graphics card. Yours would not.
That's fair. That's fair. I'm more curious about the numbers and what the numbers mean than generating the pretty picture.
Yeah, he's like ray tracing. He's like
Yeah, I'm care about the pretty
reflections and yeah.
picture. What is one thing on? I guess what are you concerned with the most on the spacecraft right now?
Ooh. Yeah, that's an interesting one. There's a few things I'm concerned about the spacecraft a lot. One is making sure that we hit our mode. We need a spacecraft that is stiff enough to, have a natural mode above 40 hertz.
What are we at right now?
Do you want me to say that number?
No.
Yes. The fuck are we at, right?
31?
We're at 31 right now.
31.
I mean, that's fine, that's
wait a minute. We weren't at 31 last week. What happened? Never mind.
So that actually lowered because we included the carbonics ring, and that goes into including things in the model and making a more detailed version. When I had my very
Oh, that's that
beginning-
more nodes thing. Man, she totally just like
And
higher
what's the
fidelity level.
solution, Holly?
make it stiff.
Make it heavier?
No. And so basically, when you look at the spacecraft, I have numbers that come from the spacecraft. Things change. We didn't have an avionics box in there for the longest time because the avionics box was not defined. So I put like a rigid spider there to hold that corner together. Well, the whole thing is going because
Can we get a spider? Like a cobweb spider kind of
It
thing?
kind
Put it
of
up in
is,
the
yeah.
corner
So
of
I
the
put
spacecraft?
a connection in that corner because we didn't have an avionics box and I needed to connect that. But it's an infinitely rigid connection. Any box I put there is going to be less than infinitely rigid. So that when I put the avionics box in there, the mode shapes changed. Additionally, I put the carbonics ring in recently, which is a ring that attaches us to the rocket ESPA for attaching us to the rocket itself. We were provided an FEA model from carbonics, and I put that in there. And that dropped our mode slightly because now there's another interface in the stack up. And so there's something else in between that can be oscillating and losing
So we're pretty
stiffness.
far off right now. We're
Yeah.
9 hertz off. And to be clear, we don't want to be at 40 hertz, right?
No,
we actually want to be
at
at 45.
45.
And that's kind of our
50
aim
would
to
be
go
even
into,
better.
right?
Right.
But this is how spacecraft engineering works. Like
Mhm.
we at one point we're above 50, and then we go, oh, that's too massive. Let's make it less stiff. And now we're too less stiff. So what is the path forward to essentially add what needs to be 14 hertz to it?
Yeah, and the interesting thing about it is when you look at the mode shapes, you get actual mode shapes. So you get to see in which direction is that oscillation happening.
So
And
you've used the term modes a lot.
Yeah.
And I'm just thinking some of our listeners,
Fair
well,
enough.
both of
Let's
them,
Take a step back.
both of
Yeah,
them.
there's one guy particularly. Those in San Francisco. I think he has no idea what we're talking about. But yeah,
Okay, yeah.
I feel like you have someone in mind there, Matt, but
no.
right.
A general.
just some guy in
Sense.
San Francisco.
Yeah.
Okay.
Yeah.
So like a mode, give us like a simple explanation of like a first mode and a second mode, maybe using a beam or a string as an example to
What the fuck is a mode, Holly?
So a mode goes back into which direction are you naturally going to oscillate? Which direction are you weakest in stiffness wise in your spacecraft or in your beam or whatever component it is? And so when you look at like a cantilever beam, it's a very long, slender beam. It's pretty much going to oscillate, not on the primary axis of the beam because it's very stiff along the primary axis. So it's going to oscillate, on the secondary, third, fourth axis, whatever axis is being.
So like
not
up and
supported.
down.
Okay, yeah.
Holly's
we'll go
giving us a
up and
very
down.
physics. Here's the thing.
So-
Just Google the Tacoma Narrows Bridge.
Okay.
You
yeah,
guys heard
that's
this
fair.
story?
Oh yeah,
That's
that's a
fair.
good
The
example.
one that
And
just
so-
oscillated with the wind. that
Yeah.
was its fundamental
Dancing-
frequency. That was
dancing
mode
gurney.
0, right? Or mode 1. Is it mode 0 or mode 1?
Mode 1.
Mode
Yeah, so
1
it
and
will
just
Dude, you're such
oscillate.
a software guy. Is it mode 0 or
I
mode
fucking
1?
know. I'm not a structures person.
Stuff doesn't start at 0. Code's
The only thing that starts at
really
0
starts
is
at
like
0,
computer code, man. Like,
right?
cut it
Unless
out.
you're MATLAB.
Oh, yeah, fair.
And so your first mode would be up and down in that case. Your second mode might be side to side. You're not really going to compress the beam at all until you get to third, fourth, fifth mode shape, because then you're going to start twisting.
So what is the mode? What is our first mode in the spacecraft?
So our first mode
Right now, anyway.
in the spacecraft is the box of Vestri basically moving the top left to right, or kind of parallelogramming
Okay.
itself.
Gotcha.
And so that tells us that the walls to the base plate isn't stiff enough.
Mm-hmm. Mm-hmm.
And
And it's potentially because we keep calling it a box, but it's not really a box.
It's
It's
not
an
a
open
box,
box because we took the top off it, which is now the
there's
side.
one face off it, yes.
Yeah, it's a 5-sided box.
And so that is part of it. Yeah, you're losing stiffness on one panel because you have a side that's open. And so a square is going to be a not very strong shape. This is why we see triangles almost all the time in engineering. You never see squares.
What are you talking about? What is it? What? Psyche is not a triangle, it's a square.
So when you,
All buildings are squares, not triangles, except for the pyramids.
yeah, but they're squares made up of triangles. So there's triangles hidden
That
in the
was
squares.
awesome.
What are you talking about?
She's
Two
saying
triangles.
we should have used struts.
My
instead
house is made out of 2x4 walls. It's not a triangle house.
No,
But it would be
there's
stronger if it was.
there's so many truss elements in your house for being able to do triangular support.
It's definitely not optimized for mass.
That
That's
is
true
that
too.
is fair. All right.
And so the mode of a spacecraft is which direction are you going to oscillate?
Yeah, yeah.
If
So
you
the
just
first
let it
one is
oscillate.
the doghouse going side to side
Going
in the
side to side,
hurricane.
parallelogramming.
What's our second one?
Second mode is the tank drum head. So
Mhm.
basically it's the tank moving up and down through the base plate.
Gotcha. So the base plate kind of oil can. Well, I guess
It's
it's
kind
not
of
oil.
trampolines.
Yeah, trampoline. Yeah, yeah.
Yeah, so the base plate kind of trampolining the
right.
tank, which is a fun one. The third one, you rip the top off of the spacecraft, basically grab the top and pull up.
Only in simulation though.
And the simulation, yeah. Fourth mode, I've called it toothpaste because you basically squeeze Vestri like a toothpaste tube. It works.
Okay, so our first mode is mode 0,
Okay.
is the box tipping over. How are we fixing it?
Yeah, so we have to investigate into ways we want to have a stronger connection in between the base plate and the walls. So we have to increase the stiffness there. So we have clips that are currently designed that connect the base plate to the panels.
I totally called this, by the way. I was
Mhm.
like, this is not going to
I
work.
did.
Is
Um,
Robin like coming in and giving himself credit?
Yep.
I'm going to also give myself a little credit on the back.
Well,
Okay,
you're the
moving on.
designer, Holly. You're supposed to give yourself
I'm not
credit.
the designer.
No,
That's the
she's
thing about
not.
it. I'm the structural analyst.
Oh, so you guys are both bashing on the
So-
designer.
No, not necessarily. But the thing is,
Kind of.
I'm given a model. I tell you what the numbers are. The numbers might be good, the numbers might be bad, but I'm going to tell you what the numbers are.
Sounds like lack of ownership.
Okay.
Okay, go back. So you have
and so-
clips.
Yeah, so you have clips to the base plate. And so those clips can get larger, they can get stiffer. You can add additional rib support in them. We have additional elements that provide stiffness brackets in the spacecraft. We have reaction wheel brackets on the top that connect our top to our sides and our top to the back. So those brackets can get thicker and stiffer as well. Additionally, we have.
She means heavier.
Yeah,
Okay.
that's what I get. Whenever
Yeah.
we say thicker and stiffer, that means heavier.
That's fair. That's fair. Additionally,
Don't
we
worry,
have
we'll make it up for higher cost.
Well, the
too.
good thing is, I mean, Ollie, on this, where are we at on our mass budget right now?
we are slightly over the mass budget at the moment.
So we're too fat and not stiff enough.
yeah, exactly.
Mm.
So we can do some sort of cross
I
brace.
feel like my pip
support.
is coming up soon.
Yeah.
We can do some sort of cross brace support across the open face to turn it into some triangles that's not a square. We can provide more corner stiffness brackets. The good thing about it being the panels that are failing in stiffness is there's a lot of options we can take to stiffen that. It just means that more investigation needs to be put into
Graceful
place
repair. Gotcha.
to stiffen those up. Something like the base plate, stiffening that up requires like a redesign of the base plate, which none of us want to do. But stiffening up panels, that can be done with additional brackets.
Okay, but just adding in brackets after the spacecraft is essentially already built and assembled.
No, we can redesign the brackets right now, or if we find that it's not good enough, we add those brackets in post.
Okay, so mode 1 we can solve by bigger brackets.
Mhm.
What about where's mode 2 at right now?
Mode 2 right now,
That's the trampoline, right?
that's the trampoline.
Yeah, but we already know what we're going to do on that.
Yeah, mode 2, I believe, was at 44.
What are we doing on it?
We're gonna change the two thruster brackets into one bracket, which is essentially going to add stiffness.
Oh, we're making a uniform thruster bracket. Okay, so
Yeah.
those won't be two independent brackets on the
Right.
bottom.
So
it'll
they'll
be one.
So it'll provide some stiffness between it. So that one's at 44 right now, which technically is above 40, but with our margin of safety, we don't want to be that close.
Yeah, no, we want to go higher.
So we want to be at 45. Is that just until we go into vibe testing, or do we want to be at 45 on launch?
I'd like to be at 45 on launch.
Why is the number 45, 40 or 45 or 35? Why isn't it 10?
So it's 40 via the SpaceX RPUG guide.
Sure. But I mean, why did they pick?
Hold on, I know a guy that used to work at SpaceX, and
Mhm.
I think he worked on the engines. Robin, why is it 40?
Throwing on the bus there.
Oh man, I totally got. Well, so SpaceX, it's not just SpaceX. All the launch providers end up predicting their models and eventually flights to get their environments. And so you do not want the spacecraft or the payloads to couple up with the vehicle. That would be supremely bad idea for everyone involved. And it actually gets more complicated, right? Because we're a ride share. So it always gets more complicated with me. We're a ride share. So we're actually, not only do we have to do our own modeling, but we have to submit that modeling to the launch provider for them to then rerun their analysis, including our model, to make sure that it didn't change their model. Just like adding one little separation ring
Yep.
lowered our stiffness by 3 hertz or 5 hertz. The same thing can happen to their vehicle. So it's
So SpaceX to the range actually submits a gigantic model of the whole rocket to say we're above or we're within compliance and we don't think we're going to destroy the vehicle.
yeah.
Yep. Absolutely.
But why you do bring up a good point, which is like we as engineers, we love to be as safe as possible. This is clearly how all engineering works, right? It's my favorite analysis of NASA, where they landed the rovers that were supposed to last for 90 days and last for 20 years. The engineers designed them to last for 20 years, right? They weren't just meant to last for 90 days. We always want to build the best spacecraft so that the structures component doesn't fail. But there's another pushback, which is if we're over 200 kilograms, we don't launch. So build a great spacecraft.
Well, it's even worse than that, Matt. If we're over 200 kilograms, I'm going to make sure we launch. So the only option that I'll have to
He
do
takes a
drill holes.
is either drill holes where they don't want me to, or unload propellant,
which is not happening. So we're drilling holes,
which is super bad.
But why make it 5 hertz above is my question. Why go to 45? Why not go to just 40 or 41? What are we actually protecting against?
Yeah, what are we protecting against? Wait a minute. I want that 5 hertz back.
No, you really don't. Because the thing is, in simulation, I'll call it 40 hertz that we're going to. If I say we're going to 40 hertz in simulation, that is probably not real life representative. We probably have some error zone there that's, plus or minus 5 hertz. So let's go to 45 to make sure that plus or minus 5 now gets us above 40. That window gets narrowed down the more physical testing we do. So maybe we want to hold 7 hertz of error. Maybe we drop that to 5. Maybe we drop that to 3, but probably not with further testing.
So we do a vibe test. We're going to do a full system vibe test on this. And let's say it comes back at 40.001 hertz. Are we good with that?
No.
Why not?
I mean, technically, according to SpaceX, we can fly.
So why would you say we can't?
Because things change over time. Like, we are guaranteeing that the craft that vibed at that exact second is 40.0001 hertz, but things change. Something might shift slightly, something might change slightly. Temperature considerations are also a big factor, because now you can have thermal expansion. Something might have more or less contact than it did in a previous thing. Environmental factors make or break tests sometimes. And so you want to have whatever factor of safety present to make sure that at your worst case scenario, you're still above 40.
Sounds like there's some more mass we could take out of the vehicle. That's what I'm hearing, Robin.
Well, I would totally, if we were really that close, I would totally go talk to the launch provider and be like, okay, what's your margin, right?
Fair
Because
enough.
yeah, if we're doing margin to be above, they also are
They
doing the
hold
same
margins
thing,
themselves.
right? So I would probably go look at that a little more
Just margin on
carefully.
top of margin on top of margin.
Yeah,
for
well,
sure.
and that's how you end up with
Over-engineered space.
over-engineered spacecraft,
We got to be perfectly engineered spacecraft to keep it light enough. That's kind of the goal.
and
Woo.
not 1 gram less.
I have one more question, Holly, which
Yeah.
is in our CAD model.
Mhm.
Every time you send me screenshots,
Yeah.
all the pictures are like this ugly ass forest green. Who chose that color?
So when you make a finite element model, the actual assembly model itself, oh, and I didn't speak on that any, but that's fine. The actual assembly model itself auto chooses the green. We use NX, which is a Siemens product using Nastran as our solver. It auto selects green. It takes a lot of effort to go in and rechange it myself, and I'd rather spend that effort elsewhere. So I'll leave it as its automatic green.
Teach
It's a
physics, but you
fine
can't teach
green.
style.
Man, I'm gonna take it back to actual engineering and numbers because
Mhm.
that's just how I roll. It's not like preference on color. There's actually a color palette for that is better supporting of colorblind engineers because a lot of
Interesting.
But
engineers are
the frequency thing we get is a rainbow. So, I mean, the base model, sure, but the actual results you get is literally a rainbow. It's a heat map, and that's not for the
Yes,
colorblind.
that's true.
Actually, it kind of is. Like there is a specific color palette to use that will allow your audience to be able to discern the differences that you're talking about in that
I'm gonna
rainbow.
I'm gonna ask ChatGPT if this is colorblind capable color palette.
Yeah, but Holly's totally right. It's a total pain in the ass to change, but we could form a committee and we could.
Now, I'm actually just gonna write a Twitter post to Siemens and ask them why the fuck it's green. How to
Yeah,
change
no,
it.
but I mean, I've changed the color before. In one of the structures blog posts I made earlier, I made everything white to make it, more pretty for your structures blog.
Thank you,
So
Holly.
More pretty.
more pretty.
Thank you.
There you go.
Okay, awesome. Thank you, Holly. By the way, you get asked one bonus question at the end. You get to ask any question you want to Robin.
And Matt.
No,
Oh,
not to me. I'm the
no,
host. Just to Robin. Okay, let's go through mailbag. First, we have a question from Carl. Robin, I'm gonna let you answer this one. Carl, who is from Sweden. I'm actually surprised because I thought they took all of August off. So guess he did a little bit of work in the middle of August.
I mean, it's September, right?
He didn't submit this today, did he? Was this submitted today or in August?
End of August.
It was submitted end of August. So
right,
I still
all right.
stand correct. After listening to the power episode, I wanted to ask if you could use excess power to do some non-mission relevant computation. Example, could you mine cryptocurrencies or do protein folding?
Technically, yes. No, it's not worth it.
I mean, if you think about it, how much is like a kilowatt solar panel is not that much. What is the cost of that? 10 cents?
Well, I mean, Carl's question about excess power is sort of the crux of the question because you have to decide like, well, what's excess power? So if we weren't using, like our spacecraft is designed to run a kilowatt thruster, and at the same time, we actually have to be thinking about the thruster and checking parameters. So we have the flight computer on, and we have reaction wheels, and we have to account for all of the different things electrically going on. So we actually, our design is in that propulsive mode. So we don't really have excess power in which to then compute something. And the extra engineering effort to then try to optimize around power would be not the way to go on a spacecraft.
Yeah, when we talk about excess power, we have a couple, maybe 100 watts of excess power.
Well, it
and
really
that's-
depends too, whether you're at the beginning of life or end of life, and how
There's a
far
lot of
away from the
variables.
sun you are,
And also thermal matters so much to how
and
much
angle,
we can use. And
like yeah. So it's, I mean, I don't want to use my famous line of it's complicated, but honestly, I really don't want to make it any more complicated. So it's not that we don't, it's not that we couldn't, but also our processor is designed for space. So like you literally could go buy a processor today that's probably faster than what we're using for the same power.
Absolutely.
Usage.
I mean, your laptop is more powerful, right? Like you could run it on a MacBook and you're going to mine more Bitcoin than you are in space. So it's just not really worth it
Yeah.
for us.
Yeah.
Okay. From Crosby, After Roid Raid's last week episode, with the Vestri mission launching next year, Holly, how do you do the CAD simulations to account for the unique stresses of landing on an asteroid?
Yeah, that's going to be one that's going to be really interesting because every asteroid is going to have slightly different surface composition. And so when you look at it, there's going to be a different like crush factor to the soil gravity and how that the soil composition and how that actually pebbling affects. So when you actually impact with something, all the ground kind of spreads out. Maybe it has more compression factor than something else. And so you actually have to run a series of different tests to try to figure out how hard are we actually going to impact, at what angle will we impact. There's been a lot of impact studies across a lot of different spacecraft that have some great heritage though. And so we can kind of build off previous test articles, data sets, and kind of take that into account.
What about micrometeorites?
Yeah, micrometeoroids are a concern. They're not my primary concern. Usually you have small surface impacts for a micrometeoroid. You might be anywhere from like 10 to 20 kilometers a second. Usually they're pretty small. If you have good enough walls and shielding, it's usually not a concern too much.
I'm pretty
Uh,
sure we don't have enough shielding.
I'm pretty sure we might not either. So yeah, it's a risk you always take. You may never run into a micrometeoroid, but if you do, you might have a bad day. There's some known risks going into space, and it's how much do you want to beef up your spacecraft for surviving a micrometeoroid versus are you sure you're going to run into one? And those
I
are
hope we run into a
trade-offs.
big ass meteorite, not a micro one. All right. This is from Symbol Owl. What level of precision do we aim for when simulating hardware? I think we kind of covered that in a lot of words already, so I'm not going to go through it. But he does make a point, which is you talked about the model after you got it from Eric not being just one
Yeah.
clusterfuck of one thing, but having all these different having all these different pieces on
Yeah,
it.
so I can.
How do you worry about the resolution of each one of those pieces?
Yeah, so what I did is I made an assembly finite element model where I basically make a finite element model of every single component that I'm going to put in the spacecraft and then put them all together, build them up kind of like Lego blocks, and I can swap out any one of them, which means that I have control over the model of every single individual component separately. And so one can be finer than another. It really depends on if it's one big, long, featureless plane. I don't need super fine precision in that. But if it's an area that's going to have some peak stress concentrations at a corner, I'm going to want more elements around a bolt hole, around a corner, around a bend, things that I want to actually investigate. What is the behavior in this specific area? And I'll put more nodes close together and more elements there, have finer resolution versus an area that's just kind of a wide open expanse of material.
This one's for Robin.
I feel targeted.
What you are you planning for all sorts of failures, and i.e. not the common ones? Are you considering alien attacks or the spacecraft becoming sentient, etc.?
Ooh, that's
I
good.
feel if your spacecraft becomes sentient, you have bigger problems.
Actually,
I actually think
I think
that's
it's the
success.
opposite.
Yeah,
Yeah,
like,
no, if
we
it
build
becomes
something
sentient,
so
we win.
amazing, it could become like I am all about.
Yeah.
Everybody's all afraid of AI, and everybody has these AI, and there's like AI safety companies. Like, I want to see somebody make Skynet. It's pretty fucking awesome. Like the Terminator was
this
amazing.
is where you and I diverge. This is definitely complementary leadership. No. Well, I mean, taking it as seriously for a moment, sure, we could always reboot the computer. So we can turn it off, turn it on immediately. Oh, I was conscious. No, you're not. Sort of like the whale in
Also, if a 3-person software team can make a sentient
Hitchhiker's
spacecraft,
Guide to
that's
the
pretty sick.
Galaxy.
What about aliens?
Yeah, aliens. Again, I feel like if we get attacked by aliens, we win.
So I want to actually bring this up because we always think of aliens as like little green men that come and shoot laser beams.
You mean like bacteria?
There's actually a realistic possibility, and I hope we find this in our solar system. We find bacteria, right? We find microbes. We find a very, very small
You
life.
recognize if we find them, we're immediately cooking them, though?
That's what I was going to say. For
That's
us,
the plan.
we are immediately going to kill
No
them.
Andromeda syndrome here.
Correct. But I do hope we find them because I think it would change the world.
I don't think we have any sensors that we would know that we found them for what it's worth because we're a mining company, not a go find life company.
Fair.
From Cosmic Arc,
Cosmic arc.
Cosmic arc. Could asteroids be safely deorbited to the surface of the Earth to be mined?
No. Next
Okay,
question.
next question. From Jarek. CAD simulations are one of the best ways to reduce risk and cost for a spacecraft mission. So he's obviously a structures engineer.
Yeah.
Of course.
We're structures enthusiasts.
Hold on. Rachel, stop clicking the fucking buttons. You just moved it out and it moved my shit.
I'm sorry, I deleted.
Please don't edit that out.
What was something you were relieved and amazed to find out you could actually simulate using CAD?
Ooh, that's a fun one. Yeah, I think one of the most fun things you can simulate with CAD is actually like multi-body models and how they interact with each other in a more complex way. And so that's looking at things that are stacked up together and sliding together, moving along one another, having friction between them. And you can actually have fully actuating components in your FEA models that unfurl correctly, that behave with their friction coefficients, that, respond to motion in that way.
Sorry, I just woke back up. Okay.
Okay, sorry.
God.
Some other fun ones. Irradiate your spacecraft, make some thermal contact models, and
I'm moving to the
figure
next
out-
question, Holly. I'm
okay.
moving to the next question. You
Thermal
had too much. There was too many lists of fun things you really enjoy about CAD software that I just can't get behind.
I get excited about
From
CAD software. I'm
Brandon.
sorry.
When you run CAD simulations for asteroid mining, how do you account for the vastly different gravity environments compared to Earth-based mining?
Yeah, that's a valid concern. Like when you look at gravity on Earth, you have a prevalent downward force of a very specific gravity that you know. And that's always going to be your biggest driving factor in everything. You know, if you drop something, what way it's going to fall, which way things are going to settle in Earth gravity. In space, it's kind of challenging because you have such a lower degree of gravity. And if you actually, drill into something, equal and opposite reactive force, you're going to be pushing yourself off the asteroid now. And the gravity on the asteroid isn't going to be enough to hold you grounded. And so you have to account for things like that. The gravity on every single asteroid is going to be different. Floating through space, even, all those microgravity effects from the asteroid around you aren't going to be localized in the same degree of freedom that Earth-based gravity is, because you're transiting around a spacecraft and where the gravity is pulling on the spacecraft changes as you orbit. And so those things are important things to consider. Even if it's a lower amount than on Earth, the spacecrafts are built to survive in space, not to survive in Earth. So we build them to space gravity. And so even if the gravity is less, relatively, it's still a critical concern.
Can we get a shirt that just says space gravity?
I'd wear it.
All right, Holly. You got one final question, and it's for Robin. What would you like to ask Robin?
Oh,
I don't like this part of the podcast.
I love this part of the
You don't like
podcast,
this
except
part of the
nobody's really
podcast?
gone hard. So if you can go hard in the paint, that'd be great.
Ooh,
Especially because I didn't give you the option to ask me a question.
okay.
I see how this goes.
If you had to redesign from scratch an entire subsystem of Vestri from the ground up, which system would you choose?
I actually think I'm pretty happy with Vestri at the moment. I think we've done a pretty good job of optimizing some of the components to do more than one thing. So like you were mentioning the brackets in the avionics box, those really serve two functions, right?
Yeah.
Like you have to hang on to the reaction wheel with some kind of bracket,
Mm-hmm.
and also using that bracket to hold together the radiator panels
Yeah.
and the avionics box, serving not only to hold the individual PCB cards, but also serving as a corner element to the radiator panels and the base plate. I think we've got a pretty good layout and a pretty good structure.
Mhm.
I'm not super happy with where the different elements of mass are allocated. I think
Okay.
we could have done a little bit better job of allocating a little less mass to our propellant tank, maybe a little more mass to our solar wings, solar panel wings. So there's a few ways that I would change where we distributed our mass around a little bit and where we expended that mass capital. But overall, I think the spacecraft's in a pretty good place, actually.
Well, it also comes back to how we thought about design on the spacecraft, which is we specifically didn't want to get locked into one design decision. This is why we can all sit here and actually make fun of the square baseplate, or even go back and make fun of the hexagon carbon fiber sandwich panel baseplate, because we were willing in those processes to say, this isn't going to work, let's change it. We could have
Yeah.
absolutely made the square baseplate work, but it wasn't the right design, and we switched it. Avionics, right? We started off with a whole bunch of boxes, then we had a couple external boxes, and we are like, absolutely not, put them back inside. And so we've been uncomfortable, I think both me and Robin, with a whole bunch of different parts of the spacecraft. We also just fucking changed it. I think that's kind of what makes us special, is we're willing to just say, this is wrong, let's make it right, and not
Yeah.
sit here and oscillate or have a design committee. Sometimes there are uncomfortable meetings on weekends, right, where everybody's got to be here, but like that's how you actually build something great.
Makes sense. Thanks.
Wow. So inspirational.
So inspirational. Okay, thank you, everybody. And what I think is the best bonus of this podcast is that Chap was not here. So
Aw.
Who?
Holly has to choose a winner. So last week we announced that we are doing a small giveaway for the person who submitted the best mailbag question. So Matt has filtered through them.
Mhm.
We did not ask all of them. Holly, what's your what was
I
your
really
favorite?
loved the question about the sentient spacecraft and alien attacks. It was a fun design consideration.
that was Symbol Owl.
Yes.
I kind of got to agree. I think that was pretty fun.
I would like to
I
know
like
who
an
Symbol
out-of-the-box
Owl is.
question.
Is this person
It's their email.
What's up with the unconscious bias against potential artificial intelligence?
if we were on, okay, here's where I get canceled by everybody. If I thought we were on a road
All
trip,
right, thanks everyone. All right, have a
Have a great
there's
day.
our outro.
done.